Today's video will demonstrate how to perform addition with floating point numbers. One performs addition with floating point numbers by, first of all, taking the left-hand side and right-hand side and making sure they have the same exponent, then adding the significand, and then combining them back together into a single number. This video will demonstrate that entire process. We'll start with a review about how floating point numbers are stored in memory. There are three fields: the sign field, the exponent field, and the significand. The real number is -1 times the sign, either -1 or 1, times 1 dot the significand, times 2 to the exponent, and the exponent is stored in the exponent bias format. To demonstrate how this works, is take a look at 4.231 times 10 to the 5 plus 6.329 times 10 squared. Now, both the left-hand side and the right-hand side have to have the same exponent, so I got to take the smaller exponent, the 10 squared, and I got to move the decimal point to the left until both the left-hand side and the right-hand side are 10 to the 5. So 6.329 times 10 squared is the same as 0.6329 times 10 to the third, or 0.06232, or 0.006329 times 10 to the fifth. Now both the left-hand side and the right-hand side are 10 to the fifth, and I can add them together. Now, using the distributive property, I can take the significance and put them together in parentheses and multiply it by a single exponent. This allows me to add the significance, and 4.231 plus 0.006329 is 4.237329 times 10 to the 5. Now, we're going to do this with a four-step process. Number one, we're going to determine if the adjent, which is the left-hand side, or the addend, or the right-hand side, has the smaller exponent. And then we're going to convert the smaller of the two, or more specifically, the one that has a smaller exponent. So both the left-hand side and the right-hand side, or the adjent and the addend, have the same exponent. Then we're going to add the significance to the two. Notice the exponents will be the same. And then finally, we're going to canonicalize it. This means we're going to take the exponent and the significand and put it into the standard format mandated by the IEEE standard. Let's take a look at step one. We're going to find which term, the adjent or the addend, has a smaller exponent. Our find exponent difference function is going to first find the exponent of the adjent and then find the exponent of the addend, and then these two will be subtracted. Now notice I have my get exponent function. This get exponent function and its complement get significant function will find the whole number exponent and the whole number significant. In other words, it's going to shift the decimal point all the way to the right of the least significant digit in the significant and adjust the exponent as follows. Let's demonstrate how this works with 5.25 plus 1.6875. We'll start with my adjent, which is 5.25 base 10. Now, the floating point representation is 0, which is my sign, which is positive, 1, 0, 0, 0, 1. That's my exponent in my exponent bias format. And then my significant has the implied 1 dot, and then all the bits for my significant. Now, in my standard format, this is 21 base 10 times 2 to the negative 2, okay? And my addend is going to do the same thing. Notice how my significant is 27 base 10 and 2 to the negative 4. Therefore, my exponent of my adjent is going to be the negative 2, and my exponent of my addend will be negative 4. When I find the difference, that's just going to be 2, which means I have to shift the decimal over 2 slots with the smaller of the two. Notice my smaller of the two is the adjent because it has a 2 to the negative 2 exponent, even though it's the bigger of the two numbers. In step 2, I'm going to convert the smaller term. Now take a look at 0.6329 times base 10 times 10 to the third. As I shift my decimal point over to the left one slot, I add 1 to my exponent. In this case, I shifted over 3 slots. Notice how 0.6329 times 10 to the third is the same thing as 0.006329 times 10 to the 6. They're equivalent. The same process works with binary. As I shift my decimal point over, then I have to add 1 to my exponent. So my convert exponent is going to take the number and the difference. So once again, I have my 5.25 plus 1.6875. Remember, 5.25 had the smaller exponent term. So my number is 5.25 base 10, And here's my floating point representation. But now my exponent is going to be the -2, and my significant would be 21, because I want the whole number version of my exponent and the whole number version of my significant. And my difference is -2. Now my exponent is going to be the get exponent, and it's going to be the whole number version plus the difference. Now my get exponent is going to be -2. My difference will also be -2. Therefore, my full exponent will be -4. And my significant will be computed by saying, get the significant, which is 21, and the difference, -2, and I'm going to right shift it by -2. And right shift by 2 is going to take 21 and multiply it by 2 squared, or 2 to the 2, which is 4. 21 times 4 is 84. And therefore, my final number is going to be 84, which is my new significant, times 2 to the -4, which is my new exponent. And let's verify we got this right. So 84 times 2 to the -4 is the same as 84 divided by 16, which is 5.25. So therefore, I'm going to have the same number I had before, but just in a different format. And more specifically, that exponent must be aligned so I can then add the significance. In step 3, I'm just going to add the significance. So I'm going to take my numbers I had before, and I'm going to get the significance of the adjunct, and I'm going to get the significance of the addend, and I'm going to add them. So let's walk through this. My sum significance will take the adjunct, which is going to be 84 base 10 times 2 to the -4, and this is my whole number version of my significant, my whole number version of my exponent. My addend will be 27 base 10 times 2 to the -4. I didn't change this one. I only changed the adjunct. I'm going to add the significance, which is going to be get significant of my adjunct, which is 84 base 10, plus get significant of my addend, which is 27 base 10, which is going to be 111 base 10. And then I'm going to return the results, which is a real number of 111 base 10 times 2 to the -4 base 10. Finally, I'm going to canonicalize it. Now take the number 0.000418 times 2 squared. The standard way to represent a floating point number is to put a decimal point to the right of the most significant digit. And that's going to require me to move that decimal point, and every time I move the decimal point by one slot, I got to add or subtract a 1 to the exponent. Since I'm moving the decimal point to the right, I got to subtract on the exponent. And so this is the same as 4.18 times 10 to the -2. And exactly the same process works with binary. As I move the decimal point over, I got to add or subtract 1 to the exponent. So how do I canonicalize? I'm going to get the exponent and the significant, and these are going to be the whole number version of the exponent and the whole number version of the significant. I'm going to find the location of the most significant one in the significant, and then I'm going to left shift the decimal point to the right location, and then adjust the exponent as well. So when I canonicalize, I'm going to canonicalize my sum, which is 111 base 10, to the 2 to the -4 base 10. So my exponent is going to be -4, and my significance be 111. And this is the binary representation of 111. Now remember, this is a 16-bit floating point number, so I have a 10-bit significant. So this can be 0001, which is going to be the 64 location, 1, which is my 32, 0 for 16, and then 8, and then 4, then 2, then 1. Add that all up, and you get 111. So I'm going to start with the most significant digit. I'm going to move right until I find a 1. In this case, that's going to be an index 6. And so my shift will be num digits minus index. So num digits is 10 because my significant bit field is 10. And then my index is 6 because that's where my most significant bit is. So 10 minus 6 is 4. So I got to shift the decimal point to the right by 4 digits. And that's going to consume the 0 at index 9, the 0 at index 8, the 0 at index 7, and it will also consume the 1 at index 6. It looks like I'm throwing away data, but remember, the significant format for the floating point number has an implied 1 dot, so that's actually by design. So now I'm going to shift everything over, and that's going to be 1 dot. Remember, I threw that 1 away. 1 0, 1 1 1 1, and then all the 4 leading digits corresponding to that shift. I also have to adjust the exponent. My exponent was -4, but I've shifted it 4 slots over, so that's -8. And therefore, my real number is 0 because I'm positive, 1 0 0 1, and that's the exponent bias format of -8. And then my significant is the implied 1 dot. Remember, I threw away that 1. 1 0, 4 ones, and then all those zeros are the resulting from the shift as I shifted everything over. And that is 6.9375 base 10, which is the sum of the values. All right, let's take a look at another example. Let's say 19.5 plus 5.875. I'm going to use the same 5-bit wide exponent field and the same 10-bit wide significant field, which is a standard 16-bit floating point number. So 9.5 base 10 plus 5.875 base 10. Here's our floating point notation for each. And then this is another representation of the same. Now my whole number exponent will be -1, and my whole number significant will be 0, 1, 0, 0, 1, 1, 1, 1. And then my whole number exponent will be -3 and 0, 1, 0, 1, 1, 1, 1 point. Now, which one of these two needs to be adjusted? It's going to be the -1 exponent. So now that's the same thing as an exponent of -3, and then I put 2 zeros to the right of that value. On the right-hand side, that doesn't need to change. So now I have 2 to the -3, because it's the shared exponent, times, and then my significance, I'm going to add them up. And when I add them up, I get 1, 1, 0, 0, 1, 0, 1, 1, base 2. So the result is 2 to the -3 times 1, 1, 0, 0, 1, 0, 1, 1. When I'm finished, I got to convert this number into the IEEE standard. Right now, my significant is in the whole number format. In other words, a significant is a whole number. But the IEEE format doesn't do it that way. It has a decimal point to the right of the most significant 1, which means I got to shift everything over by several slots. This yields 1 dot 1, 0, 0, 1, 0, 1, 1 on the significant. And since the decimal point got moved to the left by 7 slots, I got to add 7 to my exponent, and that's 2 to the 4. From here, I could turn the exponent into the exponent bias format, and then I have my final floating point number, 0, which is my sign, 1, 0, 0, 1, 1, which is 4 in the exponent bias format. Don't forget the implied 1 dot, and then my significant, 1, 0, 0, 1, 0, 1, 1, and then finally all trailing zeros after that. And that is 25.375. Okay, here's a problem for you to try your own. Try to add these two 16-bit floating point numbers. First, convert the exponent and the significant into the whole number version of each. Find out which exponent is smaller, adjust it, add the significance, and then canonicalize it. Here's another problem with two different numbers. See if you can compute the addition of these two floating point numbers. You can learn more about floating point addition in the addition section of the floating point chapter of the C++ data structures textbook.